Alright, so can you see my screen, right? So those are the thing actually we discussed in the previous class. We discussed about that some rotational kinematics, and then we start to talk about that moment of inertia, which play a major role for understanding the rotational kinematics and also the dynamics of the system. We write down some equation which is analogous to the linear kinematics, to the angular kinematics, and also the dynamics. And after that, the new parameter we discuss about that moment of inertia I actually, right? Moment of inertia for point mass distribution and moment of inertia for continuous mass distribution. And we also discuss about that two law which is called the parallel axis theorem and perpendicular axis theorem. Using these two theorem actually we will be able to find out that moment of inertia for different shape of object through different point actually. If you, let's say, if you have a disc which has a mass m and the radius is r, then if you want to rotate this system about this point at an angular velocity, let's say omega, then its moment of inertia through the center of mass should be half of mr square. And if you want to rotate, let's say not this point, if you want to rotate through about 1n, then you can also find out, because using the parallel axis theorem, if you just know the distance from here to here, let's say which is the t and this axis and this axis are parallel, then I can write moment of inertia through that side or any point. If you choose over here, let's say this is the point A, then the moment of inertia, this point A should be moment of inertia through ICM plus md square, right, which is actually the parallel axis theorem. Because we are using parallel axis theorem, these axes are parallel to each other, then it should be moment of inertia through the center of mass of this object is mr square plus m, and d should be basically r again over here, right? And in that case it would be simply 3 by 2 mr square. That should be the moment of inertia for this disc about one side. So that's how actually we'll be able to find out the moment of inertia through any point I want, if I just know that moment of inertia through the center of mass. And most of the case actually it will provide that moment of inertia through the center of mass for different shape of object. You know that moment of inertia of a rod, uniform rod which has the mass is same and the length is L through the center of mass, is moment of inertia ICM actually 1 over 12 ml square. And if you think about a ring means which has a not a continuous surface, there should be some hollow surface, right, which you can consider it has a mass is m and the radius is r, then its moment of inertia throughout the center of mass, which is I write down ICM, would be mr square, and so on. Whatever the different shape of object, we will find out. That must be given throughout the center of mass of this case. All right, let's talk about, let's say I have an system which has 3 point mass connected by 3 different massless rod. Now let's define this is the mass m1, this is the mass m2, and this is the mass m3. What I'm going to do, I'm going to rotate this system about this axis at an angular velocity omega. Then I want to know how much energy does it require to rotate that system. Since is, let's say this is that center of mass of this object, let's consider its center of mass is not moving, right? So center of mass velocity is 0, it's not moving, the total system center of mass, which means it is only rotating, it has only the rotational motion, right? If it has the rotational motion, then its total energy would be simply that kinetic energy, which would be half of I omega square, because kinetic energy we write is simply half of mv square, right? That's, we know that kinetic energy for translational part, where m is the mass and v is the velocity. In the case of rotational case, this is half. I is analogous to the m, which is the moment of inertia of this system, and omega is the angular velocity. So that's why this should be simply that kinetic energy of the system. And in how we are going to find out, we'll prove that one, don't worry about that. But this would be that rotational kinetic energy of a system. That means if the center of mass is not moving, it doesn't have any translational kinetic energy. If you plug in v equal to 0 over here, so kt, which means the translational kinetic energy is going to be 0 over here. Since it's rotating, that means it has only rotational motion. Remember, there is a difference. If a system is moving, let's say I have a inclined plane, I release a block, this block is going to slide downward, right? It has only translational motion. Translational motion, which means is center of mass, this one is moving with some velocity, right? We can write the center of mass moving. But what if, let's say, instead of this block, if I release a solid sphere or a ball, in that case it has center of mass, but it will be rolled down in that case, right? It will be rolled, and as well as this center of mass will move towards the downward direction, which means it has two types of motion. One is linear motion, which is the velocity of the center of mass, and another it has that angular motion, right? This is known actually that rolling motion. When the system has both type of motion, rotational as well as the translational motion, that called the rolling motion. You can say the example of a motion of a car wheel. When the car is moving in the road, the car wheel is rotating about in own axis at angular velocity omega, as well as its center of mass is also moving towards the forward direction. So that's why you change your position, you make a displacement. But the motion of a ceiling fan, which is above your head, is rotating. It has only rotational motion. Its center of mass is not moving in that case. When the system has both type of motion, rotational plus the translational, then it's called the pure rolling motion. It's called that pure rolling motion. In that case, it has both type of kinetic energy. One is kinetic energy. Let's write down this, the kinetic energy. Kinetic energy translational plus the kinetic energy rotational. Kinetic energy translation would be half of m v square plus kinetic energy rotational would be half of I omega square. Alright, that's called the pure rolling motion, when the system has both type of motion, rolling plus translational. Alright, let's come to our this part. How we are going to get this rotational kinetic energy. Let's say this is the case. I'm going to draw it again for you. This is that system I'm going to rotate. This is the mass m1, this is the mass m2, and this is the mass m3, which is rotating at an angular velocity omega. This is as a linear velocity v1. This would be that linear velocity v2, and this would be that linear velocity v3, which is actually, because when you're going to rotate, definitely it will make a circular track, right, over there. Then this velocity will be always tangential to the path. And let's say this is that r1, this is the r2, and this is actually that r3, which is from this rotational axis. Then I can write that total kinetic energy, it should be half of m1 v1 square plus half of m2 v2 square plus half of m3 v3 square, right? Since I have the three mass over here, if I have more than, then I will write down also summation of that way. Fine. Now over here, I know this every point mass over here has the same angular velocity omega, because all are moving at the same constant angular velocity, which means I can make a relation. This V1 should be omega into R1, V2 should be omega into R2, and V3 should be omega into R3, right? I can write down because angular velocity is fixed over here. Then I am supposed to write it should be m1 omega square R1 square plus half of m2 V2 should be omega 2 omega square R2 square plus half of m3 omega square R3 square, right? Then I can write this kinetic energy would be, if I factor out that half of omega square, then I can write this one in terms of summation notation. It should be I 1 2 3 mi ri square. Can I write down this one? Because if I plug in I equal to 1, it should be m1 into r1 square plus second time I'll write m2 r2 square plus m3 r3 square, which is, I give the limit, I have the 3-point mass over here. So that's why I start, I is the index over here, I start from 1 to 3. I'll find out this part. Now this one actually is the moment of inertia for this point mass distribution, right? That we know that from our previous class. So that's mean this one then I can write, it should be half of I omega square. So that should be basically the rotational kinetic energy of this system. Right, that's not actually the rotational kinetic energy of a system. All right, let's say I have, try to understand, this is, I have two identical inclined plane, exactly the identical. I make it identical means everything is same over here. This height, this angle, even the material is exactly the same actually. And what I did, I took two objects. One is a solid sphere which the mass is same, another actually the block with the same mass, and it is also made from the same material. Let's say both two are wooden block from the same wooden type of block actually, wooden source. Then if I release these two objects at the same time if I release from the rest, the which system will be come down first? Two scenario. One is if the surface is frictionless, and second time we'll consider the friction. Right. Let's say if the
obviously the frictionless.
Yeah, if it is the first condition is, if let's say if they are frictionless, then the which block will be come down first?
The round one or sphere one?
Round one or the sphere one. Why is so?
Sir, it will have rotational energy inside of it.
If it is a frictionless, will be rotate.
Yes, sir.
How?
Well, that's I don't know how, but it is going to rotate.
No. If it is a frictionless, then it not going to rotate, because frictional force will, without friction it cannot be rotated over here.
Okay, sir.
That's the reason. So if friction is over here, actually try to rotate the system. If there is no friction, there will be no force over here. So instead of rotating, it will be simply slide down on the surface. Right. In that case, both will arrive at the same time. Right? Because it has the same mass. This is also the same mass. It has this. In that case, it has the same amount of potential energy. Right? And it is also traveling the same distance, because these two is exactly the identical inclined plane. So which means that they will have a same kinetic energy over here. Right? Do you understand? Because this potential energy mgh is going to be simply that kinetic energy half of mv square, and both is same. This h is same, g is same, mass is also same. Then the v would be also the same in every point on this inclined plane, right? Which means they will touch the ground at the same time. So they will take exactly the same amount of time to travel this distance actually. So that's why they will reach at the same time on the ground, which means the race will be tie over here. Right, if it is a frictionless. Now what about if I include the friction?
Now the sphere will
No,
win
it's
in the race.
a sphere will be win the race. What is your logic behind that? You're on the right track. If you think properly, you can answer the question actually. You're very close. At least you are.
Sir, actually,
Go ahead.
it has its own kinetic energy, potential energy, which is transferring into kinetic. However,
Exactly.
the friction is also giving it some energy by rotating it. So it has more velocity. It will have more velocity
The
compared to the
friction will be
current.
resist that motion, right?
Yes, sir.
So that is exactly the same on the both two object.
But,
Plus,
but the friction will provide it a rotational velocity or something like that.
yeah, rotational, which means angular velocity, right?
Yes, sir.
Now the
Angular
question is,
velocity.
where does it get this energy?
From the friction.
From the friction. Friction will be provided.
Why not? Because in previous case there was frictionless, so it couldn't rotate.
The friction doesn't have that power to provide that energy. Where does this energy is
Oh,
coming in?
sir, that's coming from the potential energy,
Exactly.
which is getting converted into friction. Then friction is giving it back.
No, no, no. Friction cannot be the back
Okay, sir.
into.
Friction is the reason of the angular velocity here.
Yeah,
Then that's the
friction
story.
only the reason, and friction what is going to do? Friction will be lost the energy from the system, right? Friction is going to
Yes,
be
sir.
that deduct some energy. Friction is going to be the lost energy from here. Friction is going to be the help to rotate that one. For that's why he going to take some energy from the total system. Nothing is free. I'm saying you. The friction is going to help you to rotate that solid sphere, but in term of that, you have to pay something. You are going to pay some energy from your potential energy, which is going to be the loss from your total system, right? Are you getting my point?
Yes, sir.
Then both will be happen. That's true also for the block, because in the case of block is also acting the friction over here. So that means same amount of energy will be lost from the both two system, because we take exactly the same amount of mass, exactly the same material. So frictional energy lost by the friction will be the same for both two objects, for the block and for the solid sphere, because they have the same mass, they have the same identical mass property, identical coefficient, identical friction coefficient actually, coefficient of kinetic friction, because they made from the same material. So that's why their coefficient of static friction or kinetic friction will be the same. Yes.
So because the area of the surface of friction of the circle is less than the area, the surface of friction of the square.
Are you present in my class in the frictional chapter?
Sir?
Are you present when I'm discussing about the force of friction?
Yes, sir. Yes, sir.
Then doesn't you follow my class properly? Because I
Sir,
said
I will
that
please.
frictional force doesn't depend on the surface area. Remember?
Oh,
I said if you keep a block in that way, or second time you change that orientation of the block, in the both two cases the frictional force is the same over here, although in the first case is covering the larger surface area. Frictional force is surface independent. That's why I'm sorry I cannot accept your answer. All right. The correct answer would be the block will going to be win the race over here if it is a frictional case. The reason is I have only the potential energy, right? Which is mgh, right? That energy is going to be the kinetic energy. There will be some lost by the frictional case. That must be going to be that kinetic energy at the bottom point, which is half of m v square. Am I right? This is actually that case actually that your or you can write down this formula also solved by the work energy case, because your work done, the change of energy should be work done by the non-conservative force over here, right? So in that case we can write the change of energy means final energy minus initial energy. It should be simply work done by the non-conservative force, and then I can write work done by the non-conservative force plus initial energy must be equal to the final energy. Initially we have only the potential energy, which is we write mgh, right? And work done by the non-conservative force would be lost by the system, right? The friction is going to be the loss, because you can see that the system is moving to the downward direction. This is your displacement, but this is the frictional force. Then angle is 180 degrees, so cos of 180 degree minus 1. So that's why it's to be negative over here. When it's come to the bottom point, it has only that kinetic energy. Only the kinetic energy we will find out over here. Now the point is over here. So I have the same potential energy for both two systems. There would be the same amount of energy is going to be the loss from the system by the frictional force, because they have an identical material property. Now for the kinetic energy, when this block is coming to the downward, its kinetic energy would be simply half of mv square. That means this total energy, whatever it is, rest is going to be totally converted to the linear kinetic energy of the system. But in the case of solid sphere, we have this kinetic energy as well as rotational kinetic energy, right? So that means this amount of energy, whatever it is, let's say this is the 5 joule. 5 joule will be, in the case of block, will be totally converted to that is translational kinetic energy. And for that solid sphere, it has that translational kinetic energy as well as the rotational kinetic energy. This 5 joule will be divided over here among these two quantity, which means obviously this V will be greater than for these two this velocity, because 5 joule will be totally converted to the translational kinetic energy over here, but this time the 5 joule will be converted to the translational kinetic energy as well as that rotational kinetic energy. That's why in the case of block, the velocity of the center of mass would be higher than velocity of the center of mass of the solid sphere. That's why the block will be win the race. You understand? That's why I'm saying that if you release a block and a solid sphere in a race, if you have the same mass, the same material property, and also the two identical plane, definitely the block is going to be the come down first, because its center of mass, the velocity of the center of mass is higher. That's why the block is going to win this race. You have to think about that way. Come on, guys. Those are the so. All right. So there are a lot of yeah.
ভুল জীবন দেখে ফেলেছি, sorry.
No. Doesn't make. Why you'd be sorry, guys? It's not your fault. I said you. It's not your fault actually. The way you should think about that should be given by some instructor. The physics is the life. Come on, guys. You can explain everything by the physics. But our bad luck, we cannot keep that, or we cannot show that lighthouse of that physics for the student. That's our difficulty actually. Alright, so let's say, did you ever see that when actually the ice skater moving or rotating, how he or she rotate? Or did you ever see the dance of the Michael Jackson, right? Did you ever see to perform his dance? You'll find out in the YouTube, right? So how he actually moving? Did you ever see to dance the Michael Jackson in stage? He also know the physics. Or ice skater also. Let's give that example for the ice skater. Let's say this is actually the ice skater is dancing. So when he or she going to that rotate, how does he or she make this rotation? You will see that if you closely observe that one, when she is going to be that rotate, what he he or she actually bend his hand look like that, right, close to his body actually. When he or she is going to be the stop that rotation, he extended his hand in that way. Did you ever notice that one? You can see that one right now in your YouTube. When the Michael Jackson is going to rotate in his dancing performance in the stage, when she going to the rotate, he bent his hand look like that, close to his body. There is a reason. And when he wants to stop this rotation, he extend his hand look like that. Do you know the reason? Reason is simply that this moment of inertia or this rotational kinetic energy. When he extended this hand in that way, in that case, his moment of inertia is going to be that increase, right? You know that one, because moment of inertia, if you consider the point mass distribution in mr square, if you extend the r, that means you are taking that mass from way far away from your center of rotation, because you are going to rotate about this axis. If you take that mass from far away from your rotational axis, your moment of inertia is going to be increased, right? If moment of inertia is going to be the increase, in that case, your total energy is fixed, right? You're going to rotate this kinetic energy half of I omega square. If this one is going to be the increase, that angular velocity must be going to be the decrease. When you bend, when they bend their hand in that way, in that case, moment of inertia is going to be the decrease, so that this angular velocity is going to be the increase in that way. He can make a very swift rotation in that case. That's happened when they actually doing this ice skater or that Michael Jackson going to the rotate, they use this physics law. You should think about, whenever see anything in happening in the nature, try to understand, ask yourself why it is so, then you will get your answer. If you does not get your answer, ask someone who know this thing properly. Then you will find out this is interesting. Otherwise, you will say that's boring thing. Even though is a car is moving in the road actually, why is moving? You are supposed to explain in that way actually. Then it will be easier. Then it will be easy. Otherwise, it's very difficult or boring subject is physics. All right, let's talk about that another thing. So torque. Torque is basically a twisting force actually we use to rotate a system. Let's say you have this is also used. You use this one torque when you're going to open your door, going to inside your room. Then you use this idea of the torque actually. Torque is simply, we say, the twisting force to rotate the force actually you use to rotate a system. Let's say this is a object you are going to rotate about this point. Then what you did, you applied a force over here to rotate the system, which is at a distance the r from here. Due to that force, probably this system going to be rotated in that way, right? So this will be the position of that object after a certain time, which means you are going to rotate that system about that direction. It create a displacement over here. So that's why the torque actually we say the twisting force, and the torque we can define, it should be simply r cross f. That's the definition of the torque. Remember, this is a very crucial point over here. Never write down f cross r. That's wrong. You cannot write down this one, because you know that the properties from the vector a cross b is not exactly the same thing b cross a, right? Those are the different two vectors. So that's why you cannot write down this one. Torque should f cross r. That should be the wrong. The torque would be simply the r cross f. And it's a vector. You can find out the direction. You know how to find out. You have to use the right hand rule to find out the direction of that part. But remember, what is r? R is sometimes called the line of force actually, or sometimes it's also called the moment of r. So sometimes we say the line of force, or line of force is this one, I'm sorry. Line of force is basically this one, the way actually the force is applied, and this one is called that moment of arm actually. Moment of arm. So, but remember, when you're going to apply a torque on a system, you have to remember 2 points. One is where you are applying the force and which direction you are applying the force. Let's say I have this object over here and I want to rotate this object about this point, and I apply this force around this direction. Due to that force, will this system will be rotate? Will
No,
this
sir.
system is going to rotate?
It's going to move forward.
Yeah, it's going to move forward. If let's say it is fixed over here.
No,
So,
sir, it's not going to rotate.
the reason is the torque is 0 in that case, right? I can say, since that's not rotating, then the torque would be 0. The torque is 0. Why? Because you know that these two actually, this is actually your moment of arm. These two vectors are right now parallel. Your r is toward that direction and force is toward that direction, right? If these two vectors are parallel vector, then what is the angle? Angle is 0 degree.
0 degree.
So if it's 0, then obviously this cross product is going to be the 0 over here, because the magnitude of this cross product, we know that it should be RF sine theta. If theta is 0, then obviously torque is 0, which means the torque is 0 means that's why it's not rotating over here. Something is not rotating means the net torque is 0 on the system. So that's why it is important, if you want to rotate the system, which direction you are applying that force. Let's make a decision over here. So what about, let's say if I apply the force right now over here, again I am going to rotate about this point. Will the system will be rotated still?
So this time it will rotate.
It will be rotated, obviously, right? So because this makes an angle over here, then I can find out this is to be the force F cos theta, but there will be a component of the force to that direction, which is F sine theta. So F sine theta will be help to rotate the system about this counterclockwise direction. All right, that this time the torque is not equal to the 0. So that means it's play a role over here which direction I am applying the force. This is the first point. Second point, where you are applying the force actually. Let's say if I apply the force over here, say over here, I know the system is going to rotate. That's what I described. What about over here? It will be also rotate, right? But what about if I apply the force over here at the rotational point? Will it be rotate the system? If I apply the force at that rotational point, will that system is going to be rotate? What do you think?
Sir, it's going to rotate, I believe.
Is it?
Sir, why not?
Let's say this is your door, and this is your hands. If you want to close this door, where you apply the force? Over here or over there?
The second thing over there.
Then you are prescribing that you should apply the force at that point. Oh, come on.
Sir, well, that can also close the door, but I have to apply more amount of force.
It will be broke. No, guys, it's not going to rotate. You have to.
Sir,
if this is actually hinge the door,
okay,
then
so then you are
the knob
giving
is
the
over
force at
here to
hinge.
rotate the system, right?
Yes, sir.
Yeah, I'm saying that, yeah, if you apply that point, it's going to be the rotate. But in that case, you need apply more energy. That's why that the knob of the door is other side of your hinge, right? You never push the force over here to rotate the door, because in that case the torque is 0. Why is torque is 0? Because your R is 0 in that case. This R is going to be the 0 because you are applying the force at the rotational axis. And remember, R was the position of the force from your rotational axis or rotational point. If you apply the force at the rotational axis, then the R is 0. R is 0 means torque is 0. If the torque is 0, the system is not going to rotate. All right. So that's why it is very important actually when you're going to calculate the torque, where you apply the force and which direction you are applying the force. That's two things actually play the major role when you're going to calculate the torque actually. And remember one more point over here. we'll consider the torque counterclockwise is positive. We'll follow also that convention actually, and the clockwise torque would be negative. We'll consider the torque, the clockwise would be negative. We'll follow that convention over here to calculate the torque of the system. Alright, let's talk about, I have 2-point mass which has a mass, let's say this is M1 and this is M2, and it can be rotated about this point. And that's why I apply a force over here to rotate the system. After a certain time, it changes its position. So it will go, this would be that M1 and this is actually the M2, which means it's also create an angular displacement del theta over here. Right? You know that part. Let's say this is the AF I apply over here and this is that angular displacement. Now I can say due to that displacement is, I also say that this is actually that S over here. I can make also relation between that S over R must be equal to del theta, right? Because this is actually that curvature divided by radius, it should be angle is going to be created at the center, right? You know that one. So which means S should be R into del theta. All right. Now I can find out this work done by the definition. It should be F into S. That's the definition of the work. We know that one, force into displacement. But this force and the displacement over here, they are parallel vector. Every single point on this trajectory, they are parallel to each other because force is also towards that direction, tangential direction over here, which means the angle is 0. If the angle is 0, then I can write cos 0 actually the 1. It should be only Fs. And I also find out that S, which is actually that F should be R into del theta. Right? And I also know these work done, I can also write down also for change of kinetic energy from the work energy theorem, right? And this kinetic energy would be simply that rotational kinetic energy because its center of mass is not moving, it's fixed, which means the velocity of the center of mass is 0. So I will only find out that rotational kinetic energy, that's I write half of I omega F square, which is the final kinetic energy, minus half of I omega I square. Because its moment of inertia is same, it's not going to change center of mass actually. Then write one line, I'm going to do something over here. So I can factor out this half of I from this part, then I will find out omega F square minus omega I square, right? I can write. Let's plug in this left hand side. I'll write down F R, this part actually I write over here because F R into del theta actually I'm writing over here, F R into del theta from that definition, and this one I'm going to write half of 2 alpha into del theta. Why? Because I know that from this rotational kinematics omega F square equal to omega I square plus 2 alpha into del theta, right? So that which means omega F square minus omega I square would be 2 alpha into del theta. That's why I plug in over here. Fine. Now look at this. I can cancel this 2 and I can also drop the del theta from both two sides of this equation. Then I will find out this would be Fr would be simply into I alpha. Right? Now this Fr is going to be the torque for this diagram. Look at this. So this is actually your R and this is actually your force. They makes the angle 90 degree over here and sin 90 actually the 1. So that's why I can say that F dot R would be simply the torque of this system, which means torque actually that I alpha, which is known actually that Newton's second law in terms of rotation. Because in the linear case we write down F equal to ma. Remember I give you the analogy, m is analogous to the I and alpha is analogous to the a, which is angular acceleration. So that's why this is called actually that Newton's second law in terms of rotation. We'll write down. So that's mean the net torque on the system actually would be I alpha. All right. And from that part actually we can also write down. So let's say we are going to find out work done on a rotating object. When a system is going to rotate, then what should be the work done of this system? Let's say I have this a object over here, rotational case. It's a disc you can consider. The disc has a some point. So let's say this disc is going to rotate about this point with some angular velocity that I do not know. So I choose a point over here which is at a distance, obviously would be r, because it has the radius r, and since it's rotating, after a certain time I'll find out that should be the point over here, right? Which means it makes a angular displacement at the center. Thus I'm going to say that it is actually the d theta. This is, I can write the ds, which is the curvature of this part, and this one I know there will be also the force over here. By the definition of the work done, we can write dw would be simply force into ds. If you can write in terms of vector, these two force and the ds are parallel to each other. This is actually the ds, and this is also the force in every single point on this curvature. So that's why angle is 0 and cos 0 actually the 1. We can write in this part over here. And this ds over r, you can write, which would be the d theta, or you can write the ds would be simply r into d theta. I'm going to plug in that part over here. I can write this dw would be f into r into d theta, right? And the f are actually simply the torque of the system, we say that. So this is the torque into d theta. So that's how you write down the work done for a rotating object. It would be, or you can write down the w would be simply tau into theta. That's the work done for this rotational body. All right. All right, let's talk about that angular momentum of rotating object. I'll find out first for point object, angular momentum. It's pretty much analogous to the linear momentum. We say that if you have an object has a mass, when the system that object is moving with a velocity v, then we say that the linear momentum of a system is simply m into v, right? Let's think about for rotational case. Let's say I have a arbitrary shape of object, and that object, let's choose a axis. This is my x, this is my y, and this is my z axis. That system is rotating about this axis at angular velocity omega. Then I choose a point mass over here, which is mi. I know there will be a lot of point mass. I choose only one, which is mi, and which is at a distance ri from this origin rotational point or rotational axis. If that system moves at angular velocity omega, then I can say this point mass has a linear velocity vi, right? Because I know this one is going to rotate on this trajectory. Because r is fixed, it will create a circular track over there, which means this velocity will be tangential to the path, and this angle will be 90 degree. We know that one from our rotational motion or rotational kinematics actually, or circular motion, you can say that. All right, so now the angular momentum for this point mass we define. So that's the definition. Remember, this angular momentum Ri for this point mass. Come on, what is disturbing? Start to disturbing again. So this Ri should be, Li should be Ri cross Pi. That's the definition of that angular momentum. Remember, in general, for the point mass, we define in that way. So L actually the R cross P. Angular momentum we express by the L. Fine. Now this one I can write. I can write one more line, which would be simply Ri cross m into Vi. And if I take the magnitude of this part, I know that angle between the Ri and the Vi actually the 90 degree, and sin 90 actually the 1. Simply I can write, and in that case Ri m into Vi, right? From the vector I write down in a scalar form this one. Look at this. Don't make a confuse over here. Then I can make a one more relation with this angular velocity. Vi should be omega into Ri, right? Look at this. I didn't use any index for that angular velocity because angular velocity is same for every single point particle over here. The angular velocity is same. It doesn't make any difference. It's a constant angular velocity. So that's why I didn't use any index over here. Which means if I say the point particle 1, then it should be V1 equal to omega 1 R1. If you think about for point particle 2, V2 would be omega 2 into R2, but omega 1 and omega 2 are the same. So that's why I write in that form. Which means I can write down this one in terms of Ri, Vi, I'll write down, oh, sorry, it should be Mi. I'm sorry, this is Mi particle. Omega into Ri, which means I can write down this thing would be simply omega Mi into Ri square. That's the angular momentum for this point mass. If I want to find out for total angular momentum of this point particle inside this rigid body, then I will simply add the individual angular momentum of the particle, right? Which means I will simply summation, I will use the summation notation over here. It would be I1 to n, if we have the n number of particle Li, then you can write this thing is going to be that simply I1 to n. Li is going to be that simply that one, omega Mi Ri square, but I'll factor out this omega from this. It doesn't have any index, which I1 to n, it should be omega Mi Ri square. Now Mi Ri square is actually the moment of inertia for all the particle inside that object, right? Which means it should be simply that A over here. I'll express this L should be simply I omega. That's called actually that angular momentum for the rigid body. We'll use for the point mass the angular momentum. L should be R cross P, and for rigid object, which should be I omega. That's we define that angular momentum of the system. Alright. Alright, let's say since we define that angular momentum for the point mass distribution R cross P, I'm going to take the derivative of this function with respect to the time, dl over dt. Then I can write d over dt, it should be R cross P, right? Then if I take that derivative, I'll find out del L over del T, it's supposed to be dr over dt cross P, which means I'm using the UV formula, U my R over here and V would be the P. I'm taking the first function derivative, keeping the second function intact, which is the P over here. Plus in the second time, I'll keep the intake of the first function, which is the R, and this time I'll take the derivative of the second function, which is the P over here, dP over dt, right? Now let's write down one more line. If I write dl over dt, dr over dt is going to give me the velocity because R is the position, right? Remember when I'm going to explain the angular momentum, R was the position function. Then I will find out V cross P, I can write m into V plus R cross dP over dt. I can simply write down that's going to be that force. We know that one, right? Remember from impulse definition, force, net force on the system is dP over dt. So that's mean if you want to change the momentum of a system, you have to apply external force on the system. Now this term is going to be the 0 over here. V cross B is going to be the 0, right? The angle is 0 between these two vectors, m, V and B. M is the scalar quantity. It doesn't make any difference over here. So that's why V cross B is going to be the 0. I'll simply find out change of the angular momentum del over del T is going to be the simply R cross F. R cross F is going to be the torque, right? R cross F is going to be the torque of the system, which means if you want to change the momentum of a system, you have to apply some torque on the system. Angular momentum in the case of angular momentum, which is net torque would be simply del L, come on, don't disturb, del L over del T, which means I can write this way, del L over del T. If this means if you want to change that angular momentum of a system, you have to apply some torque on the system. What if the torque is going to 0? If the torque is going to be 0 of the system, if your torque is going to be 0, then you can say that del L equal to the 0. Del L 0 means I can write down Li equal to Lf, which means the initial angular momentum must be equal to the final angular momentum, which is also known that conservation of angular momentum. This is called that conservation of angular momentum. Angular momentum will be conserved if the torque is 0, like the linear case. Linear momentum will be conserved if the external force is 0, right? Sometimes we can also write down, since the angular momentum for the rigid body, we can write L equal to I omega, so that's why I write this on omega II is the initial, this index actually expressing over here, so IF and omega F. You can write in that way. This is also known as the conservation of the angular momentum. Most of the case, this moment of inertia is going to be the same. It's not going to change at all, right? Unless you do not change that mass or the rotational point, this moment of inertia is not going to change at all. It will be remain same. All right. There is two conditions. Let's say I have an object over here. If I say net force is 0 on the system, then what I can say, or what we can explain this way, we can say that velocity of the center of mass of the system is going to be 0, right? Which means the system is not moving. Let's say this is the center of mass of this object. If the net force is 0, which means the system is in equilibrium, it's not moving, it is stationary, or it will move at a constant velocity, you can say, right? In the case of other cases, let's say we say that velocity of the center of mass 0 means it's not moving, it is stationary at an equilibrium point. The second condition, if we say that is net torque of the system is 0, in that case that angular velocity of the system is also the 0, which means that the system in this case, when the center of mass, velocity of the center of mass is 0, but it can be rotated, right? It can be rotated, keeping that center of mass is 0. Center of mass is not displacing if the system is going to be rotated, which means this thing I cannot say that is totally static because it's rotating. But if you say that torque is 0, then it cannot be moved. And that case, it will be totally static equilibrium. And these two conditions actually call that condition for the static equilibrium. If the net force is 0 and the net torque is 0, then the system would be totally equilibrium or static equilibrium. That's the condition for static equilibrium. Remember, when you want to make a static equilibrium of a system, these are the two conditions. Net force must be the 0, and also the net torque on the system has to be 0. Then the system will be totally static equilibrium. All right? All right, let's say I have two discs over here. Try to understand. I'm going to solve a problem over here. These are the two discs. Let's say one is the disc actually that P, and the disc actually the Q. The P has a mass, the M1, and the radius actually that R1. This is actually the center of mass of the P, and the Q has a center of mass, let's say the B. It has a mass actually that M2 and the radius actually that R2. what I did, I connected them together somehow and make a composite object. So that's mean two different shape of object. I connected them somehow. Actually, I use a glue over here, very strong glue, so make them to a single object. That's called the composite object. So that's mean I use the two object over here. I can use the different two shape of object. I can let's say I can one disc, and I can also connect a rod over here. Different shape of object, we can make a composite object actually. All right. Now the question is, I want to rotate that composite object about this point A at an angular velocity omega. Let's say I give some value over here. Omega is 2 rad per second, and m1 actually 4 gram, very small object actually. M2, let's say that 6 gram, R1 actually that 1 centimeter, and R2 actually that 1.5 centimeter. Then how much energy does it require to rotate at a 2 rad per second? I am to find out that one. Since that system is not changing its center of mass, this composite object is said that it has only rotational motion. It doesn't have any translation motion, which means it doesn't have any translation kinetic energy also. That means it has only that it will be required only rotational kinetic energy, which is I omega square about the point A actually. I have that omega, which is the 2 rad per second. I have to find out that moment of inertia of this system about the point A. The only information is given the moment of inertia for this type of disc throughout the center of mass is simply half of mr square. That information is given only over here. Alright, so that's mean I can find out that energy required for this case if I just know that moment of inertia for this object, right? Then I'll be able to find out that how much energy does it require to rotate about that point. Fine, that's mean I need to find out that moment of inertia for this system about the point A, which implies that this moment of inertia, I can find out the moment of inertia A, it should be the moment of inertia of the object P about the point A plus the moment of inertia of the object Q about the point A, right? So that's mean I'm adding the moment of inertia disc P and also the moment of inertia of the disc Q about the point A, because I'm going to rotate this composite object about the point A. Fine, then I have to find out the moment of inertia for these two objects separately about the point A and also the about point A for the Q. Moment of inertia of the object A about the point A, it should be half of m1 r1 square, because this P is rotating about its center of mass, which is this one, right? It's rotating about that point. So that's why it should be half of m1 r square. What about that moment of inertia Q about the point A? We know if you have this disc which is have a mass m and the radius r, throughout the center of mass is moment of inertia actually half of mr square, which is given over here. But it's rotating at a point far away over here, which is that point, which is the A. It's rotating about this point. That means we can use the parallel axis theorem, because this axis and this axis is actually the parallel over here. And what is the parallel axis theorem? Moment of inertia throughout the any axis, it should be ICM plus mass into distance from center of mass to the new rotational axis. That's a formula, right? Then I can write this QA, it should be half of m2 r2 square, because that's the mass of the object Q that's given over here, which is m2 and of the object Q. Come on, it's not working. It's very disturbing. Plus that mass is m2 and the d from here to here, which should be simply r1 plus r2 square. Right? You can see that from this picture actually we have to find out the distance from here to here, because this q is moving around this point, which is simply the radius of these two disks separately, which is r1 plus r2. Right? So that should be that total moment of inertia. So this means the total moment of inertia, it should be moment of inertia IQA plus, sorry, IPA plus IQA. You know that parameter, if you plug in, then the total moment of inertia for this system is going to be that 4.625 into 10 to the minus 6 kg meter square, right? And the energy is required to rotate at angular velocity omega. It should be rotational energy should be half of Ia omega square. Omega is given, which is 2 rad per second. If you plug in those information over here, this kr rotational kinetic energy is going to be that 9.25 into 10 to the minus 6 joule. That amount of energy will be required to rotate this composite object around the point A at the angular velocity 2 rad per second. That's how we'll be handle this stuff in that way. Alright guys, thank you very much for your passion. That's this chapter is almost finished actually. I need to do 2 or 3 more problem. I'll do in the next class actually. Alright, so just write down your name and the ID.
Sir, I believe we have only one class left before final.
Yes.
Okay, sir. So, sir, will you give us any makeup class?
Why do you need any extra class? Why are you asking for that? Taslima Akhtar, outside of the Prague University. Did you join with your another email address?
Sir, actually, you have asked to take a few makeup classes. However, you took only one. That's why I have asked.
Not really. I actually covered that one properly. Because is that I officially I missed 2 classes actually. I make up that one. Am I right?
Yes, sir. One. Sir, it's completely okay for us if everything is coming from the syllabus.
No. Syllabus is not going to finish. If you raise your point about the syllabus, then it's a big issue. I cannot finish those part even if
no, sir. Syllabus isn't the main concern. The main concern is what is going to appear in the exam.
Why are you asking about the thing? What is coming up to the exam? If you understand your topics properly, then
like
what is coming in the exam is not a big issue.
Whatever you have taught us in the class.
Yes.
Sir, okay, sir, that's great.
Yeah. But remember, you have to understand properly. Doesn't make think that what I did in the class, exactly I will give you that same thing in the your exam. If you understand my class lecture properly, you can solve those parts. Now, be honest actually. What about your feelings about your final midterm question? Is it different from my lecture?
No, sir.
Then, but your performance is very bad actually. Average is very bad. Which means people are still writing. I do not know why actually. That's basically that. Why people do this thing, I don't know. There's someone actually write. So I said this thing lot of time in the class. So is a component of a vector towards the other direction, of one vector to the other direction. They're writing actually a cos theta something a dot b divided by b magnitude vector v by v vector magnitude. What will be it? A vector or a scalar? Hmm? What is going to give me this equation? Will it give me a vector or a scalar? Can anyone tell me? Will it give me a vector or it will give me a scalar? Come on, guys. Then what do you read in the vector? Shame on me, actually. I cannot also teach you the vector. What it will be? This equation? Analyze this thing. What is in the left hand side? Is it a vector or a scalar? Huh? Tell us. Can someone tell us what left hand side is a vector or a scalar of this equation? Oh, come on, guys. Am I with you or I disconnected? Oh God, I have disconnected.